This is Edexcel AS 2015, Unit 1, and we're doing Part 2 here, which is the electricity type questions. Part 1 included all the mechanics and the materials questions, questions 1 to 6. This is questions 7, 8, 9 and 10, which, as I say, are mostly electrical. Okay. 7a then, define the resistivity of a material. So the resistivity of a material is the resistance of a sample that is 1 meter long and has a cross-sectional area of 1 meter squared. Part B then, the resistivity of tungsten is of the order of 10 to the minus 8 ohm meters, and that of polystyrene is 10 to the 15 ohm meters. Explain the large difference in resistivity of tungsten and polystyrene in terms of charge carriers. So the important thing to recognize is that tungsten is a metal, and therefore metals have free electrons. So the tungsten has very large number of charge carriers because of its free electrons, and the polystyrene doesn't have free electrons, so it has very little in the way of charges that are free to move. It has nothing really in the way of charges that are free to move through the material. So that's why the polystyrene has a much higher resistivity. So mention also polystyrene doesn't have free electrons. Part C then, sketch a graph on figure 7.1 to show the variation of resistivity with temperature of tungsten. And it says here that it becomes superconducting at 5 Kelvin. Okay, so we've got rho there in ohm meters and temperature in kelvins. And what we would expect to see for a metal like this is that its resistance was coming down, and then at 5K there it just falls away to nothing. So I'm going to need to move this. So we should see something like that. So it's decreasing, and then at the 5 Kelvin it drops to 0. Probably shouldn't draw it just as thick as I have. I've just picked out the line tool and it came up very thick. A nice ruler showing it coming down and then it dropping abruptly to 0 is what you want to show. What is the name of the temperature at which a material becomes a superconductor? And if you check your notes, you'll see that that is called the critical temperature. Part 3, the highest temperature that has been found for certain ceramic alloys to exhibit superconductivity is around minus 135 degrees C or 138 Kelvin. Explain why the search for materials that exhibit superconductivity at room temperature between around 20 degrees C or 293 Kelvin would be a major technological breakthrough. So you sort of have to explain that getting a room temperature superconductor means that superconductors could be used without the need for cooling. So it would be extremely efficient, for example, to transmit electricity with no loss. If we could build a room temperature superconductor, we could get amazing advances in like the transport of electricity. We could create superconducting magnets. You could put massive currents through the material without generating any heat. So something along those lines. Electromotive force, terminal potential difference and internal resistance are terms used when discussing a battery. Define electromotive force. So this is just straight bookwork again, the idea that EMF is the energy converted to electrical energy per unit charge passing through the battery. Part B then, a student sets up the circuit shown in 8.1 to experimentally find the electromotive force E and the internal resistance R of a battery. The student records the current I from the ammeter and the terminal PD from the high resistance voltmeter. So this is a high resistance voltmeter, which means that we can assume that there's no current flowing when it's reading. So it goes on to ask, it says, for the circuit shown in figure 8.1, complete the table by placing a tick in the correct blocks to show how the magnitude of the EMF compares to the terminal potential difference when the switch is open. So remember that you've got an equation that says that the EMF is going to be equal to the V added to the I little r. So when no current flows, that term is not present. So when the switch is open, if we look, when that switch is open, you've only got the high resistance voltmeter connected to the cell. So there's little or no current flowing, and at that point E will equal V because there's no current to be lost, for voltage to be lost across the little resistance. And so that's really what's going on here. With the switch open, we've got E equal to V, and with the switch closed, then a current can flow. So switch open, switch closed is whether or not this term is present. Switch open, there's no current and this term isn't present. So when the switch open, E equals V. So basically we're going to be ticking here for when the switch is open. Now when the switch is closed, E has to be V plus IR. So when the switch is closed and there's a current flowing, the IR term is present and the EMF will be greater than the terminal PD. And so those are our two ticks. EMF is never less than the terminal PD, so we can ignore that column completely. It's never going to be less than. This is the theoretical source of electrical energy, and it can never be less than these other things, which are the sum of the drops around the circuit. It must always be equal to that sum. It can never be less than V. The student then obtains values here by varying R and gets a set of voltmeter and ammeter readings. So you would have done an experiment like this in class where we vary the current flowing in the circuit, and that gives us some voltmeter and ammeter readings. It says use your graph to determine the electromotive force of the battery. So, as we've already discussed, the EMF can be obtained by looking at the potential difference when current here is 0. So we want to extend this line down and find the EMF on the intercept here. So by extending it here, I'm finding that the EMF, the voltage when current is nothing, is exactly 1.80 volts. So we would mention that we're finding it from the intercept of the graph on the voltage axis, and that's the value of terminal PD when no current flows. So E equals V plus IR, and E will equal V when we make I equal to 0. So this voltage intercept is going to be recorded as 1.80. So it also says determine the value of the internal resistance of the battery. So we should really just get the equation in the form of Y equals mx plus c according to the way they have plotted it. They plotted current up the side, voltage across the bottom. So Y is going to be E minus V all over R. And if we just gather some terms to make it the right shape, we're plotting, remember, I versus V here. So we want this to look like Y is equal to mx plus c. And you can see that we're going to get a gradient of -1 over r and an intercept on the y-axis of E over r. So the gradient, which is the rise over the run, equals -1 over r. So if we put r on its own, we're going to get minus the run over the rise equal to r. So we need numbers for those. Well, we can go up to the graph and look at the run. The run for this triangle here is from 1.6 here all the way to 1.8, so it's 0.2 for the run. So minus 0.2 because it's minus the run. And then we need to look at the rise. Well, the rise isn't a rise, it's a fall. The rise comes down by 0.9, so it's a negative 0.9. Okay. And so our minus run over our rise is minus 0.2 over 0.9, and that gives us approximately 0.2. 2 repeating. So 0.22 will do. Figure 9.1 shows a number of resistors connected in series and parallel to a 15-volt battery of negligible internal resistance. The overall resistance of the circuit is 12.5 ohms. Calculate the value of the resistor labelled R in the diagram. This one. Now, in order to interpret this, you probably would want to straighten out this circuit. And so the points to note are between here and here we have a parallel combination of the 10 ohms in parallel with these three in series. So there's a combination there that we can call RP1. That's really that zone. That is then followed by a series 6 here. And then there's another parallel combination at the end between these 2 points. Okay. And we can call that RP2. So what we've got is a series combo of RP1, the parallel bit, in series with a 6 and in series with RP2. So the total resistance of this circuit will equal RP1 added to the 6 added to the RP2. So this thing here is RP1, and then there's a 6, and then there's this thing here which is RP2. And the sum of these three is 12.5 ohms. Now the quickest way to look at this is to take a look at RP2 because we know the values in it. So 1 over RP2 equals 1 over 6 plus 1 over 2. So if we take a common denominator of sixths, that means we've got 1/6 added to 3/6, which will come to 4/6, meaning that RP2 is going to be 6 over 4 if we just flip both of those fractions. And that means that RP2 is 1.5 ohms. So we've got that RP1 added to 6 added to RP2, which we now know is 1.5 ohms. The sum of that equals 12.5. So we have an equation for what we've got here. RP1 plus 6 plus 1.5 equals 12.5. So if we take the 6 and the 1.5 off the 12.5, that's telling us that RP1 must be 5 ohms. Now, if we look at RP1, what that's saying is that a 10 here in parallel with this stuff equals 5 ohms. Well, the only thing that a 10 can be in parallel with to equal 5 ohms is another 10, which is indirectly telling us that 1 plus 5 plus R equals 10. Okay? So 1 plus 5 plus R equals 10. And R must equal 4 ohms. So I'm just mentioning, the reason we're jumping to this line is because if we get an R parallel of 5 ohms, then that 10 must be in parallel with another 10, which means that the stuff on the other side, the 3 resistors on the other side, must add to 10, which is how we managed to get R there. Calculate then the current flowing through the 2 ohm resistor and hence the power dissipated in it. So I've just drawn the 2 and the 6 together here. We know that the total resistance of this bit is 1.5 ohms, and we know that the total current here coming through from the power pack, we can get that from the total voltage over the total resistance. They told us the total resistance is 12.5 ohms, so total voltage is 15 and total resistance is 12.5. We should be able to get I total here coming through from the power pack, and then we're interested in this little I here belonging to the 2 ohm. So this voltage across the 2 would be I total times this total resistance here. And I total is going to be 15 over 12.5. So V will equal that. And that gives us a voltage across the 2 and the 6 of 1.8 volts. But we're only interested in what it does to the 2. So we do Ohm's law just for the 2 on its own with that voltage across it, and we figure out the current. So this I in the 2 ohm is going to be that voltage over the 2 ohms, V over R. And that's going to be 1.8 over 2 ohms, which is going to be 0.9 of an amp. And then they want the power dissipated in the resistor, and so you could do I squared R for that, or V squared over R, doesn't really matter. So if we do I squared R, we get 0.9 squared times 2, and that works out to be 1.62 watts. Okay. So a 15 volt battery is connected to a circuit that provides a voltage out, V out, that depends on the brightness of a room. The brightness of the room is sensed by a light dependent resistor, and the LDR is connected to a 300 ohm fixed resistor to form a potential divider as shown. The resistance of the LDR varies from a minimum of 10 ohms in bright conditions to a maximum of 250 ohms in dark conditions. So it's 10 ohms when it's bright and 250 when it's dark. Those values on. So we need to use our potential divider equation, and that says that V out will be the output resistor here over the sum of the 2 resistors times V in. So something like this, where R1 represents the resistance where the output is taken and R2 is the other one. So we need to put the value of 10 in because it says we're looking for bright. And so we get 10 over 300 plus 10 times the 15 to get our output voltage. And the answer is 0.48 volts. Okay. Part B, the circuit is altered so that an external load containing a small motor is connected across the LDR. This causes a window blind to be closed automatically when the room becomes dark. The voltage across the motor must be 6 volts for the motor to close the blind. The altered circuit is shown below. So what's happening here is that there's an introduction of another object, and that messes with this resistance in the lower half here, causing the potential divider to be slightly different in its behavior. So we're basically assuming that we're at 6 volts down here. So we've got 15 in total, 6 of it's down here, there must be 9 up here. So this is like 6/15 of the entire resistance, and the other 9/15 accounts for 300 ohms. So we can represent the circuit with 300 at the top half and a parallel combination that we call RP, which consists of the LDR and the motor on the bottom half. So if we can figure out from the voltages what the value of RP is, and then do a parallel calculation to get the value of M. So if we've got 6 volts here, then there must be the remaining 9 volts here. And so we've got 6 volts here and 9 volts in the upper part. Okay, so we've got 9 volts across the 300 ohm here, 6 volts in the lower part. So there's 9 volts in this top half of the circuit. So we can do that as a calculation. If we assume that the entire resistance is like R total, what we can say is that R total equals 300 plus the parallel bit at the bottom. And we can also say that 9 is equal to the input voltage times 300 over the total. So remember, the 9 volts is here, and this is the fraction of the total resistance, 300, this one, over the total, which is this combined thing. And so we can quickly rearrange that then for a value for RT, and we get that RT must be 15 times 300 over 9. And I'm making that to be 500 ohms. And that means that from this equation, we should be able to get a value for RP, and RP will equal 500 minus 300. Which is going to be 200 ohms. So this is like the resistance of this entire lower part here. So we're quickly running out of room on the iPad here. I'm going to have to move down. So we have this kind of a situation where we have a parallel value that we have already up here got a value for. So all we're doing is recording that this is a parallel thing that we're interested in, and the value of it, RP, is 200 ohms. We were also told that in the dark the LDR is at 250 ohms, and so this parallel combination of a resistance belonging to the motor goes with the LDR to give us a total resistance of this parallel bit of 200. So we can write a parallel equation for that. So we have that 1 over RP equals 1 over 250 plus 1 over the resistance of the motor. So 1 over Rp minus 1 over 250 should be 1 over the resistance of the motor. And then we just put in Rp, we know that it's 200. So we get a 200th minus a 250th for 1 over Rm. And we do that, we get 5 minus 4 over 1,000, taking 1,000 to be a common denominator, which is 1 over 1,000. So if 1 over Rm is 1 over 1,000, then Rm must be 1,000 ohms. So that's our final answer. And that's the end of the questions. I hope this has been helpful. Thanks for watching. The first part of this exam, you might remember me saying at the beginning, was uploaded as a separate video. Okay, this is questions 7, 8, 9, 10 that are mostly electrical. The mechanics and materials questions were 1 to 6, and they are in a different video, so you can have a look out for it. Thanks again.